The Agenda in the Summer with Nam Kiwanuka is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.
The Big Dipper, the Seven Sisters, Saturn, and Mars. Wonders in the summer night sky are eternal. All week we'll find out what's out there with astronomer Bryan Gaensler, astrophysicist Nathalie Ouellette, aerospace engineer Walter Stoddard, and physics and astronomy professor Matthew Johnson. Tonight, galaxies, stars, and supernovas. That's next on The Agenda in the Summer.
Nathalie, we were talking before we started taping about the reaction to the James Webb telescope because on social media, I found that it was probably one of the first instances when people from all spectrums were actually excited and they were happy or they were just in awe of what was happening. Mm-hmm. But you said something interesting. Can you tell us what you said?
Yeah, so I work a lot with the comms team at NASA and the CSA as well. And they sort of did a study of all the key words of these social media posts about the telescope launch. And they was identified as being 80 to 90% positive words, which we were overjoyed about because that means people like the mission. But when they looked a little bit deeper into the more negative words, it wasn't negative feelings about the mission. It was more sort of anxiety or angst about the vastness of the universe and sort of how small we are and how insignificant maybe they felt next to this big tool that's going to solve all of these big questions.
Do you find that in your line of work that people do get a bit nervous or maybe just feeling a bit like inconsequential with how big the universe is, so we kind of push away from trying to understand it more?
Yeah.
Yeah.
When I was a graduate student, I told my roommate at the time about my research, and she said, never tell me about that again, because I find it terrifying. So yeah, definitely I've experienced that.
Well, we're going to add to that anxiety, or maybe just some edification, but how big is the Milky Way when we talk about the Milky Way, Bryan?
So the Milky Way is pretty big. It took us a long time to figure this out, but the Milky Way is a collection of, depending on who you ask, 200 to 400 million stars and all sorts of gas and all sorts of other stuff. And if you could somehow step outside our Milky Way, it would sort of overall look like a giant fried egg. And it's sort of got this bulbous part in the middle, and so the rest of it is quite flat. And if you sort of measure it from one edge of that flat disk to the other, it's about 100,000 light years. So a light year is the distance that light can travel in 1 year. At the speed of light. So it's about 10 trillion kilometers is 1 light year. And it's 100,000 times 10 trillion light years. So even if you could build a spaceship that could travel almost at the speed of light, which we cannot do, but even if you could, it would still take 100,000 years for that incredibly fast spaceship to go from one edge of the galaxy all the way to the other. So it's this unimaginably large beast. And it wasn't until only about 100 years ago, which is not that long ago, that people recognized that there were other things outside the Milky Way. It was so large that people said, wow, this thing is so big that this has to be the only thing there is in the universe. There's just no room for anything else. And so it's this stunning realization, I think, in the 1920s, that we're just one of zillions of galaxies, some of which are much bigger than the Milky Way.
Walter, I see you nodding.
Well, and what's amazing about that is that we have figured that out, right? We've got that approximation. We figured that out from the inside. Like, we've never left the Milky Way to take a picture, right? We've never left it and measured it because it's so vast. And so just from sitting inside it and looking outward, we've pieced together some of this puzzle to figure out its size and scope and shape.
Science is so amazing.
Yeah, it's a bit like figuring out how tall you are without looking in the mirror, or like trying to read what's written in your hand with your hand glued to your face. It's pretty hard.
That was a great analogy.
Yeah, you must have tried that before.
But that's how it feels sometimes. When you're trying to establish just how far away is that gas cloud, that's what it feels like sometimes. It's really frustrating. We know the distances to other galaxies. much better than we know the distances to some of the objects in our own Milky Way.
Well, I have an image to show you of the Milky Way. Here it is. It's a long exposure image taken from the International Space Station, 271 miles above the Indian Ocean. Earth is below, with an aurora to the lower right corner, and rising from behind it is part of our galaxy. When you look at that image, can you tell where we are in the galaxy?
So a scientist hundreds of years ago tried that exercise, Herschel, and he did it by trying to count out all of the stars in the sky that he could see, and he saw that some areas were sort of more concentrated. And so he sort of mapped out this really rudimentary kind of shape of what he thought the galaxy might be based on the position. And we do see with the Milky Way, there is a concentration in one particular plane where it's brighter and there's sort of this like weird dark dust lane going through, and that's sort of the pancake or the disk that Bryan was mentioning before. So that's sort of what we're seeing slicing through. And so by looking at the configuration of the stars in the sky, we can sort of tell that we are inside of that disk or that pancake. And then we are trying to measure out things between the distance between us and some of the other stars, and we're saying, okay, we're about 2/3 of the way out from the center. We're not at the center, but that's incredibly complicated, and it's only in really recent decades that we've been able to do that, and we're still refining that measurement with certain missions like Gaia, who is trying to map out these distances to millions and millions of stars around us and trying to place us in that context.
How do you, because I, as a person who doesn't understand how it all works, I feel like, oh my gosh, what's out there? But when you're looking, how do you feel? Like, what do you see?
So people often ask me, like, aren't you like getting vertigo? Like, isn't that like freaking you out a little bit? Like you get sort of like a sense of anxiety, and to me, it's all the opposite. I love looking up to that kind of stuff because I know that we're made of stardust. The fact that we're here is because a star at some point exploded or went supernova, and that created the elements, the carbon, the gold that we have here, the calcium that created life here. And so we're connected to something so much bigger. And so humans don't often or always make smart decisions here, but I'm comforted by the fact that there's this greater world out there where our little mistakes maybe don't matter quite so much. And so I feel very comforted when I look up.
But when you said that we're made of stardust, that was very comforting for me. I don't know why that feels comforting.
I'm glad.
What do you all think when you look at the sky and see that?
Curiosity, just wonder, like, what is that fuzz in the sky, right? And then you dig deeper and you find out so many interesting things are out there. I mean, Gaia was mentioned. So one of the discoveries is that of Gaia, the Gaia mission, that's really exciting. You know, you think of the Milky Way galaxy as an object or some monolithic thing, but it's not. It's made up of clumps of stuff that are all orbiting, just like we are orbiting around the sun. And sometimes that stuff gets stripped apart in these giant streams. And then we can study those streams and learn about the structure of the Milky Way. Another really exciting thing is the first pictures of the black hole at the center of our galaxy from the Event Horizon Telescope. Being able to do that, to build a telescope that is literally the size of the entire Earth, that can see something that far away, as Bryan was mentioning earlier, hundreds of thousands of light years away, and getting a look at it and learning about it and seeing what's around that black hole. I mean, there's just so many layers behind that picture to learn about. It just never ends. Like,
we're going to talk more about black holes, but Walter, what about you?
Wow. And I said it maybe a few days ago about the idea of awe and wonder is the right response, right? Like, and I can understand fear and feeling small. Humility is an amazing thing to make sure that you never lose, right? That sense of humility, that sense of understanding that there is a bigger picture than just ourselves. But at the same time, it's a beautiful place, right? The universe is a beautiful place. We have a very special spot in it. And remembering how special we are, as well as being humble enough to realize there's something bigger I think that's the response I have and the response I encourage.
It's kind of cool too to know that you come from something bigger than you can explain or understand, right? Like, I have another image that I'd like to share with you all. This one was taken with the James Webb telescope of the Pillars of Creation. An image was captured with the Hubble telescope in 1995 and a sharper image in 2014, but this one is from 2022, taken with Webb, 6,500 light years away in the Eagle Nebula of our Milky Way. That looks like it's out of like a Marvel movie. Yeah. It's just so breathtaking. Nathalie, what is significant about this image?
So I have two answers for that, one scientific and one personal. And so if you see what Hubble saw in the visible light of the Pillars of Creation, you see that same sort of hand, but you see a lot more gas and dust that's blocking out the view of all of these stars that are being born in the stellar nursery, essentially. And so the magic of an infrared telescope like Webb is that infrared light actually passes through the gas and dust in a nebula like that. So you gain sort of like X-ray vision, but infrared vision. And so you can peer inside these dusty caverns where these stars are in just the first few millions of years of their formation, and you see the birth of these stars. And you can't do that with another tool other than Webb right now. It's really wonderful. But for a personal note, this is my favorite picture that's been taken by Webb up until now, and that's because I grew up with the Hubble picture of the Pillars of Creation, and it made me want to become an astronomer. So I'm thinking of all these wonderful images that the JWST is now releasing to the public, and I hope that there's a new generation of astronomers who are being inspired by it, and maybe they will eventually work on the next mission after Webb.
I'm also guessing that this image also gives new insights to scientists.
Absolutely.
What are those insights?
Yeah, so like I mentioned, the birth of stars, they're a little bit mysterious because as stars are being formed, they're all in these sort of what we call molecular clouds. So it's a bunch of gas, and that blocks out the visible light of the star as it's being formed. So you have all of this gas that's collapsing on itself from the gravity of the star, and you can't really see what's going on. It's like a bunch of dust all flying all over the place. But because of the magic of infrared with Webb, you can have a better view of what's going on inside. And the birth of a star is quite violent. It's not just neatly packing together material. It'll blow out material, it'll blow out energy that shocks the environment. It has these shock waves in the gas around it as well, and it can sometimes change the molecules around it. So having that insight of being able to see through that gas and dust with the infrared light helps us to better understand how these stars are being born.
And I'd love to get the reactions from everybody else. Brian, when you look at that image, what do you think? What goes through your head?
Well, when I was a student, which is around the time that Hubble was launched, we didn't know much about how stars formed. And I remember one of my professors telling me, you know, stars like to do it in the dark. And it was just this continual frustrating picture, as Nathalie described, that like you just cannot see what's going on. And the fact that we now can sort of start to see this sort of key process that pretty much drives the whole universe. Like the universe would sort of run down and sort of run out of puff if there weren't new stars exploding and splattering the galaxy with chemical elements and sort of heating up all the gas and all the rest of it. So making a star is sort of the most important thing that the galaxy can do. And the fact that we can now actually see it happening is almost a sort of a spiritual thing for me.
And Matthew? What excites you about that image?
I'll just come back to the curiosity and wonder. It's just so beautiful. I am a theoretical physicist, so I'm not an astronomer, and I never really thought too carefully about stars, to be quite frank. But it is one interesting and kind of amazing fact about stars is that in the history of the universe, you know, most of the stars have already been formed, right? So here we are, lucky enough that we're still living in a time when stars form, because most of that happened a couple billion years ago, actually. A couple billion years ago is when most of the stars in the universe were formed.
Would you say the universe is dying? Is that
I don't think it's dying. No. I don't think it's
past its peak.
It's past its peak?
Yeah.
It's like us, man.
Well, that's like
Speak
a
for
real.
yourself over there.
That's a real measurement, right? Like what we call cosmic noon, when the universe was creating stars most actively. That's in the past. That's several billion years in the past. So, yeah, I guess you could say it's past its prime.
Looking good still. Walter, what excites you about that image?
Well, looking at the image, it's not just where, it's when, right? Like when we look at it, how far away is it? Is also how long ago it is, right? Because it takes that long for light to come to us. So yes, we're watching stars being born back then, which is kind of neat.
So we're seeing the past in the present.
Yes. In fact, technically we always are, right? But like the distance that we're apart, it's insignificant for the speed of light, but it's not instantaneous. There's still time it takes for the light to reach you. And so the further out we see, the further back we're seeing.
Telescopes are time machines.
Yeah, that's right.
Yeah.
Oh my goodness. I have another image for you to see from Webb. This image is based on information from Webb of a planet called WASP 39b. It's an artist's illustration of the planet with its star in the background, exoplanet, planet beyond solar system. This one is approximately 700 light years from Earth. And this is based on the interpretation of information from the James Webb telescope, seen here in various charts that show its atmospheric readings, if I can say that word. Nathalie, can you explain what these readings are and how we got them?
Yeah, so this is really exciting in the exoplanet world. And Canadians were part of the discovery team for that, some of my colleagues at the University of Montreal. So studying exoplanets is a very tricky business because they're very far away, number one, and they're orbiting stars that are much brighter than them. So typically, the way that we spot an exoplanet is not by looking at it directly, but by looking at the effect that it has on the star that it orbits. And one of the best ways to do that is if the planet happens to pass in front of the star, you'll see sort of like the equivalent of an eclipse. We call it a transit, and the light from that star will be less bright momentarily, and so that tells you something blocked that light. But if you have a planet like WASP 39b that has an atmosphere, some of the light will the starlight will stream through the atmosphere of that planet. And depending on the different molecules, the atoms, the stuff, the chemicals in the atmosphere, some of the light, specific colors, will be absorbed by that atmosphere. And that's what we read. We call it a spectrum, transmission spectrum, which is that sort of scientific graph that you showed. And so all of those bumps and wiggles become sort of like a barcode that we can read to identify the molecules and elements inside the atmosphere of this planet, 700 light years away. And what they discovered there was the most complex sort of menu of molecules we've found for a planet yet, which includes water vapor, carbon monoxide, the first detection of carbon monoxide outside of the solar system ever, potassium, the same potassium in our bananas is on this planet. We know that, sulfur dioxide. So we know that from 700 light years away, because of the Webb telescope.
Matthew, you mentioned black holes before, so I wanted to kind of get in there before we run out of time. What is space-time before we talk about black holes?
What is space-time?
Yes.
That's an awesome question. Space-time is a construct that we have invented to explain gravity.
So it's not real?
That's a great question. It's a mathematical construct that does a great job at explaining reality, at explaining the things that we see. I'm not sure if reality is a giant rubber sheet that
I'm getting more nervous now.
that is manipulated by these objects with mass and cause bodies to orbit and whatnot. But it's a really darn useful analogy, at least, that helps us predict things like the orbits of planets or the behavior of light around black holes, for example. Yeah.
Walter, you were nodding?
Well, like that's the can of worms, right? Like, are we talking about the bending of space-time, which, as you say, is a construct? Is it really happening, or is there something else to explain it? Right?
How do we know?
I think we don't ever know. I mean, it's part of part of science in general is that we keep observing and we keep building explanations or theories for the things that we observe. And as long as we're curious and observing, inevitably, we will learn new things. And sometimes those new things require new ideas to explain them and new theories. So,
and more questions, I guess.
Yeah.
If space-time is a construct, then how are black holes formed?
Okay, so black holes are something that we think results from the collapse of a really massive star. So there are other kinds of black holes. Maybe we get there, maybe we don't. But the run-of-the-mill black hole is kind of the end of the life cycle of very massive stars. They explode, and then a possible remnant of that explosion is a black hole. And the way to understand it is it's kind of a point of no return, okay? So the surface of a black hole is something we call the event horizon, and it's not a physical thing you can touch or reach out to. It's a boundary. It's the place past which not even light can escape the gravitational attraction of the stuff that made that black hole, okay?
Well, when I think of black holes, and hopefully you don't judge me for this, I think of Bugs Bunny. Do you remember when they had that episode with The Martian? And then you had this huge black hole, and then it just went whoop into this little, like, black circle.
Yeah, classic.
Yeah, right? Thanks, Walter.
You're welcome. Yeah.
How do black holes work?
To some extent, a black hole is the simplest object in the universe. And I've heard some people say black holes are the only thing in the universe that we completely understand, because they're just the gravity. It's just something pulling on everything else, and that's it. Like, they don't have. There's not black holes of different colors or of different compositions. They're all just the same simple thing. What gets really complicated and what we don't understand is how black holes interact with their environment, because when black holes suck things in or things fall into them, it's not like just dropping a penny into a well. It's more like water swirling down the bathtub, going around in these circles and getting faster and faster. And that turns out to be this very complicated process, because there's all this friction as it gets faster and faster, and that heats it up so it glows. And then the other thing we don't really understand is that some of the stuff falls into a black hole, but some of it actually gets shot out at right angles to the direction it's swirling in at a significant fraction of the speed of light. So it's totally counterintuitive. We're sort of told black holes are things that sort of suck things in, and yet some of the most energetic ejections in the universe, these incredible blasts of energy that travel for like 1 million light years, are actually coming out of black holes.
What are the other black holes? You mentioned there's other black holes.
There are so many black holes.
There-
And now we know that there are, every day, every week, we are finding new black holes.
Yeah. What is that, when we're talking about all these new black holes and gravity, what does that mean for our notion of space and time?
There's a lot left to figure out, to learn, I think. I think that the advancements we've had in recent years in terms of the study of black holes has been amazing, with things like the Event Horizon Telescope. Now where we can actually directly see that's the thing. You can't really see a black hole because light doesn't bounce off of it. So you're seeing what's around the black hole, but you can see up to the event horizon. You can sort of study what we call the accretion disk of all the material swirling around the bathtub that Bryan mentioned. You can see that more directly now. And now we even have gravitational waves that we can measure with things like LIGO, where black holes are crashing into each other and causing ripples through this construct of space-time. So there's still a lot to learn, but I think that the tools that are being developed now, for the first time in humanity, we have really good tools to find out more about these complex objects.
Why is it important for us to understand how they work and why they work the way they do?
Helps us understand gravity in a completely fundamental way. It is one of the forces of nature, and like Bryan was saying, it's kind of the purest incarnation of gravity. It is just gravity, yeah. It's not stuff plus gravity, but it's just gravity. And if we understand black holes better, then we can learn more about this fundamental force.
One of the big issues that we have in physics right now, there are fundamental forces that we've sort of determined in physics. We have electromagnetism, we have gravity, we have two nuclear forces. But one of the issues we have is that quantum forces, quantum physics doesn't play well with general relativity, which is mostly because quantum happens at very, very small, tiny levels, like atoms, very small scales. Whereas general relativity, you have huge things, massive things, like galaxies, entire galaxies. And typically that's okay, because a very massive thing is rarely a very small thing. But there are two instances I can think of where that's not true. Black holes are very massive, very small. Or the Big Bang, you have everything in the entire universe that's very small. And so I think better understanding an extreme like a black hole might help us sort of conciliate these two forces that don't play well together right now in just physics theory.
Well, part of that problem is there's no particle for gravity, right? Because we have force carrier particles for the other forces, but there's no gravity particle, right? The graviton, or whatever you want to call it. If we find that, then maybe we can fold it together. But right now there's no gravity particle.
What about singularity? What's a singularity?
It's literally just singular. So in the description of a black hole, right, you have all your stuff in just one point. So it has no dimension. It's just squished down. It's singularity. It's a single, just one. Is there a better way to say that? Like,
it's the place where the theory stops working.
Yeah, that's
you know
right.
how I was mentioning before,
right. Yeah.
you keep discovering and looking and
Divide
looking
by
and looking,
zero,
and you
yeah.
find a place where your idea no longer works.
That's
the place where your idea no longer works.
It's the last sort of here there be dragons sort of part of astronomy and cosmology.
Yeah.
Well, this has been a really fascinating discussion. I know people at home are getting a lot from it, as I am. Really appreciate your time. Tomorrow, we're going to pull out even further, and we're going to talk about the universe. Thanks so much for your time. We appreciate it. Our guests all this week are
Bryan Gaensler, director of the Dunlap Institute for Astronomy and Astrophysics, and Canada Research Chair and Professor at the University of Toronto. Astrophysicist Nathalie Ouellette, who is Deputy Director of the University of Montreal's Trottier Institute for Research on Exoplanets, and Outreach Scientist for the James Webb Space Telescope in Canada. Walter Stoddard, researcher programmer and longtime science communicator at the Ontario Science Centre. And Matthew Johnson, Associate Professor of Physics and Astronomy at York University and Research Associate Faculty at the Perimeter Institute for Theoretical Physics.
The Agenda in the Summer with Nam Kiwanuka is made possible through generous philanthropic contributions from viewers like you. Thank you for supporting TVO's journalism.